So, welcome back, and welcome back to the 10th video on this linear algebra exercise series, which is essentially the last one. We'll have another recapitulation video, but it's going to be a little bit different from this format with like exercise and solutions and detailed solutions. In this case, today we have more exercises on eigenvalue, eigenvectors, but we also explore an application of such concepts. But let's start. We'll be encountering these concepts while working out the exercises. So, sorry. The first one. So we have a matrix. Sorry. So now it's okay. So we have a matrix, and we ask for which t is it diagonalizable. So we recall that the matrix P is diagonalizable if there exists a matrix, well, diagonal matrix D and an invertible matrix S such that S minus 1 BS is equal to D. Okay, so how do you try and diagonalize a matrix? You do this, as you know, as you probably already know, by looking at eigenvalues and then eigenspaces, and if we are lucky, we can find the basis of eigenvectors, and this basis will form the columns of this invertible matrix S. So let's try in this case. So eigenvalues so we solve this polynomial equation. So we have determinant of 1 minus lambda t0, which is very easy. So it's just this, from which we find gives. Okay, so we have just one eigenvalue, and we'll have to look at the eigenspace. So recall the eigenspace is given by, in this case, vectors such that a minus I, which is, well, it's lambda I for lambda equal to 1. Okay, if you want, this is also the kernel of a minus lambda I for lambda equal to 1. Okay, fine. So we just solve a linear system, so we have to solve this is 0, t 0, 0, x, y equal to 0, 0. This gives ty equal to 0 and, well, 0 equal to 0. So this only one. So now be careful. So if t is different from 0, then ty equal to 0 implies y equal to 0. In this case, the general solution xy is then x0 if you want, so x10. So E1 AT is the span of 1, 0. Okay. And otherwise, if t is equal to 0, then ty equal to 0 gives 0 equal to 0. So you have no condition on y. So no condition on y. And no condition on s, on t. No condition on t, on x, sorry. So any xy is a solution, and we can, and well, of course you can write this and this. So we conclude E1 of A0 is equal to the span 1, 0, 0, 1. Very good. And yes. So we know from the theory that we need a basis of eigenvectors. So if t is equal to, is different from 0 here, we just have one eigenvector, so it's not enough to make a basis. Whereas here, we actually have two eigenvectors. But look, well, if t is equal to 0, this is actually just the identity matrix. So, well, we already know that it's diagonalizable, right? So we conclude AT is diagonalizable if and only if t is equal to 0. And a diagonalizing matrix is S equal to the identity, because I mean A0 is itself the identity. So okay, and that was it for this first one, for this first exercise. So it was just not very difficult, but yeah, still. So the second exercise, it's a little new. So let's read it. So we have a country, which is not important. We have two Henry companies, and strangely, we have this research, and it shows that there are probability of flying with A and B, and they are determined by the experience of the previous flight, just the previous flight. Really the previous flight, not the previous flights. Just so if you fly with A once, then you choose again A with this probability and B with the other probability, so 1 minus this. And if you fly with B, then the next flight you choose A with this and B with this. So this is called a Markov process. It's not really important that it's called this, like this, but it's another, if you want, another exercise on organizing data with the matrices. So let's think. So let's put as usual. Here we have our input A and B, and here we have our output of this, let's say, this process. So say we know that, say we fly with A, then we fly again with A with 1/3 and B with 2/3, right? Say we fly with B, and then we have one like this, right? Okay. Okay, so actually this is it. This is your matrix A, which expresses, like, at every time one flies, they choose this A or B according to this matrix. So now the second The second question is probably a little more interesting. So assume that one first flies with A. So let's recall, first fly with A, what does this mean? It means that if you have a vector, then you choose A with, if you want, with probability 1. So if this is like A and B, you have A with probability 1. So this means flying with A. I ask, what is the probability that they fly, that this guy flies with A again on the 5th flight after this? And the hint is use eigenvectors. Well, let's have a look. What does the problem ask? Actually, the 5th flight after this, it means 5 iterations of this matrix, right? So if you take this and this solves. So yeah, in principle we know it. Here, look, we have five iterations. So the 5th flight after this, and the first, and and we started with A. So in principle we know it, but well, perhaps computing A to the 5th power just by matrix multiplication is not the best thing to do, and it becomes very, very bad. And yeah, a computer can do it, but we are smarter than computers, and so we devised a technique which enables us to work it out and actually use eigenvectors and eigenvalues. So let's follow this hint first and just make some computations about these eigenvectors and eigenvalues, and then let's see how can we use these to find this value. Well, perhaps someone here, if you recall the definition of diagonalizability here, and perhaps you think, well, if I put A in a diagonal form, then it's easy to compute the 5th power of a diagonal form, right? That's a good idea, but there's an even similar way of doing this. But let's just do this. So we find eigenvalues. So we have to compute the determinant of one. Sorry, this is going to be just a few computations. Okay, so which is minus. I hope I'm not making mistakes here. So let's solve this, and so it's 1/6 minus lambda third minus lambda this. Okay, so it's lambda squared minus 6. This is 2 plus 3, so this is 5. Minus 1/3 plus 1/6. So this is what? This is 2 minus 2 plus 1 minus 1/6. Okay, hopefully it's correct. So let's solve this. Let's solve the equation. Put this to 0, equal to 0, and look. Well, okay, this is equivalent to saying that. So the solutions, let me see, it's going to be 25. No, sorry. 10 over 12 plus or minus square root of, well, 25 plus 24. I hope so. So it's, well, this is something's wrong. Wait. Wait. Something's wrong here. I knew I was going to make mistakes. I knew it. So let me check this again. Yeah, because yes, now it's okay. So it should be fine. So one is 12 over 12, which is 1, and the other is 5 minus 7 over 12, which is minus 1/6. Okay, that's correct. So we have lambda 1 is equal to 1, and lambda 2 is equal to 1 minus 1/6. Okay, very good. So let's look at the eigenspaces. So E1 of A. So we need to solve the linear system which linear system? Which linear system? So you substitute 1 here. So, well, 1/3 minus 1, 2/3, 1 minus 1. Oh, well, first let me compute this. Suitable. So let me compute this, which is, well, minus 2/3 minus. Okay, so this is the system we want to solve, namely this. So we know that actually it's just one equation, because you already know that one is, if you look at one, the other is redundant. So I mean, this is redundant. So from this you find that one can find that y is equal to y is equal to 4/3 x. So the general solution is going to be xy, any x, and then 4/3 x. So you can like do this 1/4, but you can also do like, I mean, you can rescale. It's okay. So you can take like 3x and I don't know, 3/4. So if you prefer integer numbers. So indeed, the E1 of A is the span of this 3/4. Okay, this is it. So let's look at the E minus 1/6 of A. So that's another computation. So first compute the matrix when lambda equal to minus 1/6. It is this. Okay, 1, 2, 3, x, y equal to 0, 0. Okay. Fine. So yes. So well, just have to compute this 1/3 plus 1/6. It's actually 1/2, and this is 2/3. So this is 1, 2, 1, 2, 2/3 x, y equal to 0, 0. You know, you immediately see that you have just one equation, so it's like just this. equal to 0, which gives x plus y is equal to 0, so y equal to minus x. So the general solution, if you want, is like this, x minus x. So you take x here, 1 minus 1, and you conclude that here, well, let me put this in a different color. Well, good. Okay, so I can avoid. So here, e minus 1/6 of a is the span of 1 minus 1. Okay, very good. So we know we have actually a basis of eigenvectors. So how can we use it to assist us in our computation? Well, recall that eigenvector means if V is an eigenvector, means that AV is equal to lambda V for suitable eigenvalue. So, well, if you take A and you apply 3, 4, right? Was it 3, 4? Yes. Then it's like 1 times 3, 4 is again 3, 4. And this is nice, right? And you see that if you iterate a to the nth power, you can see that, well, if you iterate this, a squared, well, it's a applied to a, this is again a 3, 4, 3, 4. What about the other? And you see that for any n, you can imagine that this gives again 3, 4. What about the other one? So 1 minus 1, this is minus 1/6, 1 minus 1. What about a squared? This is a. So it's a minus 1/6, 1 minus 1, but 1 minus 1/6, you can put it here. So it's minus 1/6 to the second power, and again 1 minus 1. So in general, if you can compute a to the n, to the eigenvector associated to 1/6, you just put the eigenvalue with the suitable power, and then, so you see that along eigenvectors, the powers of the matrix are very easy to compute. You don't have to know this expression, but since you just know this property, then you know this, and this is very important. And also, we have a basis of eigenvectors. So the clever thing to do, since let's write it. So since we want to compute a to the 5th power 10, we try to express 10 in terms of the basis of you know a basis. What is a basis? A basis is a linear independent system, family of vectors which also generates. So it means that any vector can be expressed as a linear combination of the basis vectors in a unique way. So we just have to solve a linear system, which is this linear system, x yes, 3, 4 plus y 1 minus 1. And now it's like just a linear system, so it's like 3x plus y equal to 1 for x minus y equal to 0, which you can solve, well, for example, if you add the two equations, you get immediately that 7x is equal to 1, so x is equal to 1 over 7, and y is equal to 4x, so it's like 4 over 7. Very good. So we know that 1, 0 is equal to 1 over 7, 3, 4, this vector, plus 4 over 7, 1 minus 1. Okay. Now, we want, this is actually what solves the thing. We want a to the 5th power 1 over 0. So, which is, well, we don't have to compute this now, but we have this equality here. We are being clever, so it's like this. Sorry, this is not a fraction, okay? Wait. Okay. Okay, fine. Okay. Yes, but we know that this is eigenvector associated to eigenvalue 1, and this is eigenvector associated to eigenvalue minus 1 over 6. We know from the discussion before that this is, we already know what this is. So a to the 5th power is like 1 to the 5th power this, so it remains this. And here you get a minus 1/6 of the 5th power 1 minus 1. And the problem asks, what's the probability of flying with a on the 5th flight after this? So remember that if you take a vector, I mean, the answer here, you have this, it's a vector, this is a vector, and the first component is the one related to A, and the second is the one related to B. So look at the first component. Look at the first component. So it's what? 3 over 7 plus this, so which is actually sorry, I'm just checking. Yes. Okay. Okay, so this is it. And this is the answer. Well, you can put it in a nicer way if you want. So, namely, well, I don't know, 4, 7 times like this, and then you can like compute it. Okay, this is it. This is it for the second question here. Okay, so we used eigenvectors and we did a computation in a clever way. Just to say, you could, of course, also use we could in principle also use the diagonalizing matrix S. So put the first 3, 4, so 1 minus 1. We know that S minus 1 AS is diagonal, but what diagonal? So we have 1 and minus 1/6 here. So A is equal to S, this, S minus 1. Okay? Okay, so, and a to the 5th power, if you do this, it's like you don't have to compute a lot of things, so it's just the 5th power of this diagonal thing. But the 5th power of a diagonal matrix is very easy to compute. So once you know, you can compute the S minus 1 and find a to the 5th power easily. And then a to the 5th power 1, 0. Okay, very good. Very, 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 very good. Very good. Okay, well, it's very similar actually to doing this. This is like this thing we did here requires a little less of effort, because it's like we just look at how to express this in terms of this and this, whereas here you want to invert a matrix. Well, it's not even that difficult. It's just a 2 times 2 matrix, so, well, it's not that strange. You can do this, and then you have to do this matrix multiplication. But they're actually similar procedures. Well, they both give the same answer. Okay, now comes the final question here. What is the probability of flying with A on B that one eventually finds? Well, what's the theory about this? Well, can be quite if you look into your book, perhaps you'll find that the result is, well, you have to look at the eigenvector associated to the first to the eigenvalue 1. So this. And then make it be so that the components add up to 1. So for 3, the answer, I mean, if you know the theory, 3, 4 is the eigenvector associated to the eigenvalue 1, but you want it to be such that their components add to 1, so it's like probabilities, so 3, 7, and 4, 7. So this is the eventual probability of flying with A, and this is the eventual probability of flying with B. But, well, this is the theory, but indeed, if you look at what we've done here, I mean, even if it's not completely rigorous, but, well, let's say instead of computing a to the 5th power 1, 0, we compute a to the 5th power, a to the nth power, let's say, 1, 0. I mean, actually, the doesn't change. So you just have to replace a n where you had a 5. So it's actually just 1 over 7, 3, 4, plus 4 over 7 minus 1/6 to the nth power 1 minus 1. Now look, you see that if n is very big, then indeed this vector here converges to 3/7, 4/7. So actually we already see that after some iterations you actually converge to this. I mean, this is not a proof, but this is if you want, it's a way to check that it's a reasonable thing. Namely, the part of eigenvalue 1 remains the same, so gives you this 3 over 7 and 4 over 7, which is the final answer. And the other eigenvalue was just minus 1 over 6, which has absolute value. less than 1. So if you take n very big, then this part becomes really small. But you can see also here, even in the fifth iteration, actually the probability here of flying with A is already very close to 3/7, which is the eventual probability. So the answer, whereas of course the answer of flying, the eventual probability of flying with B is the 1 minus this. Of course, we had just 2 options. So you see that even here it's really close. So, well, if I want, I can give you like a hint for an exam. If you say you're desperate and there is not much time, and exercise tells you compute this probability after, I don't know, 5-6 iterations, but you don't have time to do this computation here, perhaps. But still, you know that if you compute the eigenvector corresponding to eigenvalue 1, you have an answer. And I mean, any answer you get for like a finite number of iterations is not probably going to be very far away this eventual probability. You have an error, of course, and perhaps you don't want this, but yeah, still. So you can give an answer saying, well, I didn't have time to do the precise computation, but I know that it's going to be reasonably close to the eventual probability because of convergence of things. Okay, so we made it. It was not too bad. So now, as usual, let's write the solutions nicely. So the first, add a page here. Oh, sorry, page here. Oh, what did I do? No, it's okay. Okay, so exercise 1. As happened before, we allow ourselves to avoid recopying and redoing a lot of straightforward computations, assuming that we attach the drafts together with the clean solutions. So, but we have to justify this result. So here we can say this: the eigenvalues of A T sorry. Well, but here perhaps it's so easy that it's even better. We compute solving determinant of 1 minus lambda 0, 1 minus lambda t is equal to 0, namely so is it correct? Let me check. Yes. Okay. We find lambda equal to 1. Nice. Fine. Okay. Lambda equal to 1. Okay. And okay. The eigenspace E1AT is given by equal to the span 1, 0. Was it so? yes, if t is different from 0 and span 1, 0, 0, 1 if t is equal to 0. And here see the drafts for the computations. Well, perhaps here you can say, well, is it so nice to avoid? Well, the tricky part here is that if t is different from 0, you know, you have this, you have to be careful, you can divide, but if t is equal to 0, then this gives the other result. But I mean, look at these drafts, they're not so bad. You can, it's okay to attach them and then write just, in this case, the solution, the clean solution is just like a resume of the result of the computations. But yeah, it's you really need to attach your drafts in this case. If not, then it's like you're not like you're saying this, you're saying you have these results, but you're not justifying them. But we don't have to recopy everything. If the style is not too bad, here it's quite readable, it's okay. We can say that in this case the draft is not so bad. So we just take this solution as just a resume. So we conclude is not diagonalizable. As I said, I repeat again. I repeat it again. There's not a rule of writing these solutions. It's really think of the reader. Think about the reader, and think about their experience, and make and write a solution so that their experience is the best, is as good as possible. This is your goal. There's nothing, and you have a lot of freedom in doing this, but you have to keep in mind the final goal. Here it's perfectly acceptable to give a solution here as a resume of the results and attaching this computations and drafts, which are indeed quite good. So it's okay. So the reader can refer back. It's still quite readable. It's okay. We assume that I claim that it's a nice experience a nice experience for the reader to go through this. If they don't want to accept these computations like here, they can go back and look at the computations. They're quite readable. It's okay. It's okay. But it's up to you. You have this freedom. So just keep in mind, make the reader feel as good as possible. As well as possible. Perhaps, well, in English you should say as well as possible. Well, whatever. That 8 is not diagonalizable for t different from 0, and it is diagonal t different equal to 0. Well, okay, fine. So, okay, in this case the solution was just like we wrote a short resume of the computations, and yeah, and referring back to the actual computations here. We are going to attach in any case. Okay, so the second one, it's going to be a little more involved, but okay. Okay, exercise 2. So 1. So the first part Okay. Here, the required matrix is A. Let me see. Okay, 1/3, 2/3. And to be clear, here put the input A here and B here and A here and B here so that it's clear. With this notation here, it's clear that the first column refers to A and the second column refers to B and the first row to A and the second row to B. So it's clear. Okay. It's synthetic and it's clear. So true. Okay. By solving determinant of A minus lambda, we find out A has eigenvalues. I mean, the computations here were quite straightforward. Say in the exercise 1, I decided, well, even if the solution is like just a resume, but computing the eigenvalues was so straightforward that we could put it here and it was still very short. But here we would have to like do these tedious computations. So we can refer back, and it's okay. And it's okay. We can refer back for the eigenvectors and for the eigenvalues. Lambda 1 equal to 1 and lambda 2 minus 1/6. The corresponding eigenspaces are given by E1 of A is the span of 3, 4. E minus 1/6 of A is the span of 1 minus 1, if I'm not wrong, right? 1 minus 1, 3, 4, it should be okay. Okay, 1 minus 1, 3, 4. Yes, very good. See the drafts for the computations. Okay. The required probability is given by the first component of a to the 5th power 1, 0. Okay, now, I mean, you see, we don't have to redo all the computations, but it's good that we explain all the passages. So we express 1, 0 uniquely as a linear combination of the basis, which form a basis. Namely, we solve linear system 1, 0 equal to x 3, 4 plus y 1 minus 1. Okay. Okay. We find out x is equal to 1 over 7, y is equal to 4 over 7. Okay. Using, and this is important, using that a to the 5th power of 3, 4 is again 3, 4, and a to the 5th power minus, okay, is this. This is important to mention. We find, let's go there, A510 is what? Let me check. 1734 plus, and there should be, taking the first component, perhaps we should mention that yes, here you put an A here and a B here, so that it's clear that flying with A is the first component, flying with B is the second component. Okay. Okay, so it's in accordance with this, and it's clear. Okay, taking the first component, we find the desired probability, which is 3 over 7 minus, and there was this number here. Well, let me recopy it. Minus 4 over 7, 6. Well, that's, I think. Oof. Yeah. Yeah, fine. Okay, this is it. I didn't put the... Okay. Okay. So the third, of course, we don't have to, we can invoke the theoretical result. So we know the third was asking what is the eventual probability, so of flying with A or B that one eventually finds. So we know from the theory, and we can restate it, we know that the eventual probability flying with A or B is given by rescaling oh, sorry, what happened? What happened? Oh no. Something happened. Something strange happens here. Oh, sorry. By rescaling the to eigenvalue, well, not the, but let's say any. I mean, it's a basis of eigenvectors, but I mean, you have many choices of bases, not just one, associated to eigenvalue 1, so that the sum of its components is 1. So we take 1 over 7 times 3, 4 This is probability. Say so. Let's write. So this is A and this is B. So eventual probability. Well, wait. So eventual probability of three over 7 and eventual yeah, this is it. This is it. We have to manage to reference to the we didn't put reference to the drafts here. We should have. So see the drafts for the computations. See here, see drafts. No, this doesn't need anything, so this is perfectly, it should be okay. So you see here that it was a kind of not so strange solution writing this time, but we decided to refer to draft sets for some tedious, straightforward computations, but we have to attach them, so we attach them. And the rest, yeah, it's kind of, yeah, this is it, more or less. So I hope it was nice, and I hope it was clear. And as I said, there should be another video for this series, but it's going to be quite different. So we'll see. In any case, now we've covered actually all of the main concepts in a basic linear algebra course, which I'm actually giving exercise sessions for a linear algebra course for bachelor computer science students. We don't learn vector spaces and more advanced things, but just exercises on matrices, determinants, and eigenvectors, eigenvalues, and orthogonality and stuff like this, and some application as we've seen today. So it's all for the basic sessions, and as I said, there should be something more, but we'll see. In any case, thanks for watching, and